Evening, ladies and gents, molecules and macromolecules. I'm your host Saizi, and tonight we are diving into sticky, stretchy, and sometimes suspiciously shiny world of polymers.
Let's meet our first category, polymers by source. Starting off strong with natural polymers that is made by living things. We are talking DNA, rubber, and maybe even your late night tears. Then we have the synthetic gang, which is nylon, polyester, and plastic. Basically, the lab-born legends. And lastly, give it up for the semi-synthetic, like cellulose estate, Nature's Remix Edition.
Now we'll be talking about polymers, so we'll cover their structure and bonding, how to draw them, and why they are solid at room temperature. Now, polymers are a huge and diverse group of different substances, and they make up of all sorts of things. What they all have in common though is that each polymer molecule is made up of lots of smaller units called monomers. For example, polypropylene is one of the main polymers in plastic, and a single molecule can be thousands of atoms long. But it's actually made from these monomers called propyne, which have the formula C3H6. And if you line a few of them up, you can see how they could keep adding together again and again until they form a huge polymer chain. Now, the important thing to be able to do is notice that a particular molecule could be a polymer and identify the repeating monomer. For example, you can tell that this polypropylene we just could make be a polymer because we can pick out a small section that seems to repeat. Then, once we have identified this repeating unit, we can draw it out by itself, and you often see the letter N in the bottom right corner, which represents how many of those repeating units there are in the overall polymer. So, if we wanted to write a reaction for combining 400 propane monomers, and then instead of drawing out the entire polymer as a product, which would take us ages, we could just draw a repeating unit and put 400 in the corner. In general though, we just put N instead of actual numbers. The other thing to notice with these repeating units is that we always use curved brackets and we show the bonds coming through the brackets. Now, the last thing we need to look at is the melting and boiling points of polymers. The bonds within the polymers are all covalent bonds which are really strong, and so would require really high temperatures to break. However, to melt or boil polymer, it's not actually these covalent bonds that we need to break. Instead, it's the intermolecular forces between the separate polymer molecules. And these intermolecular forces are much weaker than covalent or ionic bonds. However, because the polymers are so long, they have a high surface area, and so there are lots of these intermolecular forces, which means that to break them all would still require quite a lot of energy. So, although polymers have lower melting and boiling points than giant covalent structures like diamond or giant ionic structures like sodium chloride, they do have higher melting and boiling points than simple molecular substances like oxygen or chlorine, which only have a few of these weak intermolecular forces between each molecule. And this is the reason why polymers are generally solid at room temperature.
Okay people, now let's talk about structure. No neutral planar is a linear polymer. So, what is a linear polymer? It's long, straight chains like HDPE, simple and solid, no drama. Then there's a branch polymers, side chains everywhere, LDPE the extrovert of the plastic world. But my favorite is cross-linked polymers. It's a tight-knit family. Think that like it's giving you a squad goal. So, how are these things made? So let's talk about polymerization. Addition polymerization, like snapping Lego bricks together, no math, just a monomer magic.
We're going to look at how we can make addition polymers using alkenes, with a focus on how to draw the monomers, the repeating units, and the polymers. The feature that makes a molecule an alkene is the fact that it has a carbon-carbon double bond, like we can see here between the two carbon atoms in this ethane molecule. Because of this double bond, we said that alkenes are unsaturated. And under the right conditions, the double bond can break into a single bond, which allows the two carbons to form new bonds with something else. So if we had 3 ethane molecules, and all the double bonds open up, then they'd be able to form new bonds with each other, and so combine to form one long chain, which would then call a polymer. Now one way to represent this reaction would be like this, where we show all the ethane molecules, which are our monomers, on the left, and draw out the entire polymer that they form on the right. The problem with this technique though is that this reaction can sometimes involve hundreds of monomers, so to draw out all of them would take forever. A better way to do it is like this, where we show a single monomer on the left and a single repeating units of our polymer on the right. And when we say repeating units, all we mean is the group of atoms that are repeated throughout the polymer and contain exactly the same group of atoms as a random monomer, so in this case 2 carbons and 4 hydrogens.
Let's jump to condensation polymerization. A little more dramatic. It's like, here's your new chain, but say goodbye to water.
Like all polymers, condensation polymers are made up of a lot of individual monomers. With polyester though, a common combination is to use 2 different monomers. A dicarboxylic acid monomer, which contains 2 carboxylic acid groups, and a diol monomer, which contains 2 alcohol groups. And as a quick aside, if you haven't seen these colored rectangles within molecules before, they just represent the rest of the molecule. And we tend to use them in general, examples like here, where we don't make things complicated by showing the specific molecules. In order for the 2 monomers to combine, the dicarboxylic acid has to give up its OH group and the diol gives up a hydrogen atom from its OH group. And when these 3 atoms combine, they form a water molecule. This leaves this carbon from the dicarboxylic acid to bond directly to this oxygen from the diol. And it's this bond that we call the ester link.
Alright, science friends, let's speed things up with the thermal behavior round. Okay. What is thermoplastic? They chill, heat them up, mold them, cool them down for reuse. Okay. And PVC is makeover queen. Okay. Then we've got the thermosets. No second chance here, like melamine. Once it's set, it's done, like baking a cake.
And now, let's play What's That Polymer? Alright, let's start off with, it is stretchy and bouncy. What do you guys think of it? That's right, it's called an elastomer, like rubber bands and tires. Next, it is super strong and can be found in your t-shirts, ropes, and activewear. It is called a fiber. Think of polyester or nylon. That's right. Next, moldable and reusable. Melts when heated and hardens when cooled. You got it. That's a thermoplastic. Like PVC, acrylic, and your favorite water bottle. Lastly, it is stiff, unchangeable,
and won't even melt under high heat. Can you believe that? That's right, it is thermoset. Once it's set, there's no going back.
Stay curious, stay
Clever and stay sustainable.
And stay away from melting point.